I'm very pleased to be your moderator for the session today. It's being jointly sponsored by the Joint Program and by the Laboratory for Aviation and the Environment here, which is in the Department of Aeronautics and Astronautics here at MIT, which is where we sit today. And the topic is direct air capture. And this is an issue that's really important and coming on year to year. I think because countries, companies, others have declared these net zero targets. And when they began to look seriously at net zero targets, they began to realize how hard it was to get emissions out of some critical sectors. And once they saw that, then the question is, how can we meet any net zero targets? What's the net part? And people look first, well, there's trees. We could plant trees, nature-based solutions. It's not enough. That in turn to an area that's come on year after year of net energy technologies. And one of those is direct air capture, which is the one that we're talking about today. And the question is, well, it's certainly technically feasible. We're doing it. Is it economic to do it, and under what conditions? And we have really a great combination of three people to bring that topic to the table, and then we'll have question and answers and discussion after. So we're going to start with Professor Steven Barrett, who's a professor here in this department and the director of the Laboratory on Aviation and Environment, and to kind of set the stage. I mean, why do we care about this issue? Why is it so important? And I think it's important to start off to get the broader context. And then I'm going to turn to a long-term colleague, David Keith from Harvard. He's a professor of applied physics in the Department of School of Engineering and Applied Physics at Harvard, and also jointly appointed in the Sloan School. And he's been out as a promoter of this technology. I would even say, going back a few years, maybe the lone champion for a while, but has been at this for a long time on this technology, not just in research and experimentation, but also forming a company that raised substantial amounts of money to do prototype scale tests of various approaches to this. So we'll go from Steve to David. And then we'll turn to Howie Herzog. Howard Herzog is a chemical engineer, 30 years of experience in the MIT Energy Initiative here, and now a senior research scientist in that group. Deep knowledge of the chemical engineering aspects of large-scale engineering and chemical engineering technology. What's involved in going to scale with these technologies? So that's the way we'll go. I think we'll start with Steve. He would lead us into this. I think I'll go directly to you, David, if you would, and then to Howie, and save your questions. And when each of them have gotten their material out, then we'll have a broader discussion, question and answer with you, and also with those of you on the web. We have someone to try to collect your questions, and they will also come to me as moderator. So I turn it to you, Steve.
One thing is, I think we'll switch the order based on the discussion that Seb had. So after me will be Howard, then David is what I understand from Seb.
No discussion until the end.
Yeah, no, that's fine. Great. So thank you all very much for coming to this. It's a fascinating discussion, and I should start by saying that the experts are here, but my job here is to sort of say, why does this matter? Just generally, and also from, you may have noticed you're in an aeronautics and astronautics department, not Earth, atmospheric and planetary sciences, but close enough. There's some words in common, and so. Okay, so affordable direct air capture, myth or reality? And the question I want to address first is, does this question matter for the future of the planet? The framing I want to start with is balancing the CO2 budget. Now, will have all heard about targets for emissions rate reductions and things like that. But if you take a step back, it's really not the rate that matters, but it's the total emissions that we ever put into the atmosphere. Now, if you get into sort of the weeds, what I'll say isn't quite true, but let's just take a sort of simplification for now and say that if you dump CO2 into the atmosphere, it just stays there. So what that means is that it's the rate that matters, the accumulation that matters more than the rate. So this chart here shows the total ever CO2 emissions from 2020 onwards as a function of time, and then the estimated temperature change that results from it. And you can see there, an orange line stay less than 1.5 degrees. It's an aggressive reduction target. You can see there a total plateau by 2060. You can see if we don't achieve that and continue to emit, you can see a line there for staying below 2 degrees. But if we sort of fail to meet the trajectory for the orange line, but still want to maintain 1.5 degrees, you can see another line there, the black line, which implies negative emissions in the latter part of the century. So one of the use cases of direct air capture is, not destroying the planet and keeping us at some temperature threshold. Indeed, if you look at the IPCC AR6 scenarios, all the scenarios that keep us below 1.5 degrees involve CO2 capture in some sense, and those are those ones shown in the bottom there. So it really does seem that direct air capture or other negative emissions technologies are central to the future of a sustainable planet at the levels agreed by the global scientific community of 1.5 degrees or less. So that suggests that this is a profoundly important thing we need to work out. Well, what is direct air capture? Well, I'll leave it to the two domain experts to describe in more detail in subsequent talks. But the idea is we take a stream of air from the atmosphere, treat it in some way which will be discussed, such that the stream of air leaving going back to the atmosphere has less CO2 in it, and the CO2 has been removed, and then something is done with that, and that's the question, what's done with it? So the two things you could choose to do with that stream of CO2 that you remove from the atmosphere, we first, as I alluded to earlier, treat it as a negative emissions technology. In other words, take the CO2 from the atmosphere through direct air capture and put it into long-term storage. An alternative to that, which I'll come back to as to why that is important, particularly when you're in an aerospace engineering department, and it's important to me, is direct air capture as a source of non-fossil carbon for future fuels. So let's start with the first case then, the direct air capture and carbon capture and storage as a negative emissions technology. Well, in order to evaluate what makes this cost competitive or cost effective, we need to look at the competing technologies and the counterfactual. So, what else could you do for negative emissions? And what if you just did nothing and accepted the cost? So let's take the first comparison point, the social cost of carbon. This is the damage to the world done by each ton of CO2 emissions that are emitted. And there's a wide range of estimates of that. As you'd imagine, it's a hard thing to work out. This estimate here comes from a model that's from my group here in the department and led by Florian Rogan and Carla Grobler has done a lot of work on this. But it's consistent with the widespread of literature results that are out there and draws on the overall literature in a way to be a consensus estimate. So this gives an estimate that a ton of CO2 today causes around $150 of damage to the global economy and environment. Now you can see there a big range. That blue bar is sort of the main uncertainty range. Lots of uncertainties, very hard to estimate. These numbers will never get perfect, so to some extent we just have to live with them, and they'll give us some sense that clearly we should spend more than $10 to abate a ton of CO2, but we probably shouldn't spend more than $1,000 at this point because there'd be better ways to use that even environmentally. So $150, maybe up to $800. Numbers like 350, if you look out a few decades ahead, that gives you a sense of how much money should you spend to take a ton of CO2 out of the atmosphere and store it. Another thing you could do there is compare it to the competition. So the competition, perhaps in the nearer term, to direct air capture would be BECCS. So this is bioenergy with carbon capture and storage. The idea here is that you grow some biomass, switchgrass or some crops, or there's large debate as to what you might use. Through growing the biomass, carbon dioxide is taken out of the air through photosynthesis. It becomes part of the biomass. You then burn the biomass. In so burning it, you generate heat. You use the heat to generate electricity. And then the burning of the biomass releases CO2, which you then capture and store. So there's a very wide range of estimates of the cost of BECCS. I've given some here in this chart, and that gives you again a sense of the range of prices for direct air capture that will be competitive with BECCS, and it's in the sort of a few $100 range. Now I should say the BECCS does have some fundamental limits that direct air capture probably doesn't have. So even if BECCS is optimal in some sense nearer term, you probably would still end up looking to direct air capture beyond that. So just to make that more concrete, what does that end up as the direct air capture cost? Well, it's taking the average of the social cost of carbon. You end up at about $138 when you take out the cost of carbon transport and storage. So that just gives you a point number. Again, lots of uncertainty. If it's $350, that still would be useful, but it shouldn't be $1,000. So the second use then is not direct air capture as a negative emissions technology, but direct air capture is a source of carbon. So why would that make sense? Well, some of us noticed we're in an aerospace engineering department. No digs intended, of course, but it's and if you look at the energy requirement by aviation in mid-century, here's some estimates here: 20, 30 exajoules by mid-century. I've seen higher projections than that as well. Now, the IPCC say that 50 to 300 exajoules per year is the potential primary bioenergy that could be achieved mid-century. Now, that's a technical estimate, and if you include policy and other constraints, probably it's on the lower end of that, if not lower. Certainly, I would imagine it's very much on the low end of that, if not lower. Now, then also going from that bioenergy potential to jet fuel, you lose a factor of 2 in the conversion efficiency. So let's say we take the number 50 for sake of argument, divide that by 2, then you're at 25. And so you can see that aviation alone, let alone all of the other uses of biomass and bioenergy in mid-century, has taken up the entire usable supply to create biofuels for aviation, which most people believe is the future, assuming you don't want to use fossil fuels in mid-century for aviation. So that suggests that at some point, and you could argue as to whether it's 2050 or 2070 or whatever it might be, at some point, aviation's demand outgrows the possible supply of biofuels for aviation. And so you need to either use synthetic fuels or hydrogen, essentially. And that's the big question. So if we take sustainable aviation fuels made from biomass as the competitor for direct air capture, this is the range of prices of sustainable aviation fuels that are low carbon, $1–2 per liter. If we were to use electricity to both run direct air capture to get carbon out of the atmosphere, to make hydrogen, and then to combine that into a hydrocarbon synthetic fuel to put in the aircraft, then this is our estimated cost, about $2.1 per liter. That then leaves you around $80 per ton for the direct air capture if it was cost competitive with the biofuels. So that does probably tell you that we should use the biofuels first, but at some point that will run out, and then we need direct air capture and power to liquid for the aircraft. Either that, or we reinvent the entire aerospace system to use hydrogen and deal with all the risks and challenges that entails. So there are obviously many uncertainties in this. Another one could be, what if power to liquid technology advances significantly? Then you do end up with slightly better numbers. $110 per ton could be used for the direct air capture, and that looks a little better compared to estimates of the costs. So to summarize then, we need the innovators represented here to create for the world direct air capture that's $100 to $300 per ton of carbon. If it sustains at a high number, $500, $600, $700, it doesn't probably help the future of the world. But if it's numbers on the lower end, then we really have a viable solution to not only have a negative emissions technology that makes sense, but also potentially create a long-term future for hydrocarbon fueled aviation, not to say there isn't an alternative there. So I'll end with that and hand over. Howard, you're up next.
Good afternoon, everyone. I want to talk to you today about a process engineer's view of direct air capture. Before I came back to MIT 30 some odd years ago, I spent 10 years in industry, basically doing chemical process engineering. So I'll use some of my skills, analyze this. First, let me say a few words about negative emissions in general. I think they have a very important role to play in achieving our net zero emissions target. But when it comes to going net negative, which a lot of people are talking about today, I think that's premature to talk about, and actually a very big distraction from where we are today. I say that because in order for us to get to net negative, we first have to get to net zero. And so there's a lot of reasons we want these negative emissions to get to net zero without having to complicated with this net negative. And decades from now, when we're approaching net zero, however many decades that is, we have much more information to make informed decisions about whether we continue on past net zero into net negative. As Steven said, direct air capture is just one of many negative emissions technologies that are under development. All these have opportunities, and all of them face challenges. The focus of my talk today is going to be the process engineering challenges faced by direct air capture. And in this talk, I'm going to quantify some of these challenges. And then since everybody's interested in numbers, I'm going to give my direct air cost range for what I see direct air capture in 2030. So this is what a generic direct air capture process looks like. Basically, it's based on sorption and desorption. You have sorption at low temperatures as exothermic, and then at high temperatures you have desorption, which is endothermic, where you regenerate your solvent for reuse and then free up your CO2. You need energy input. You can have some energy recovery in here, and generically, this is how the systems work. Steven mentioned the systems. A lot of people are calling this solid systems and liquid systems. As a working in the carbon capture business, I like to call it a weak base system and a strong base, being the characterization of the solvents, and the weak base system use amines. And for direct air capture, these amines are impregnated on a solid substrate, and it's an adsorption mechanism. For the strong base systems, you use hydroxides, and this is a chemical absorption system, and you use an aqueous solution. You see a big difference in regeneration temperatures for these systems here. So the leading process for direct air capture, just like with regular carbon capture and storage, are based on sorption, desorption. So there's one big difference that just drives everything, and that's the concentration of CO2 in the gaseous stream that you're trying to capture it from. In air, that's 0.04%, and that's about 300 times more dilute that you see in a coal gas flue, about 100 times more dilute than in a natural gas flue. And this has big consequences. And two of the major consequences we see are, first, you need large amounts of air to be processed. If you're going to capture a ton of CO2, we can calculate that exactly, and in just a moment I will. Secondly, there's going to be a fairly significant work requirement. There's a minimum work requirement, and we're going to need multiple times the minimum work in real processes, and this leads to significant energy requirements. So once again, I'll quantify that. And as I say in the first sentence here, these are two major and they're non-negotiable challenges. So let's take a look at air processing. Just to make sure we're all on the same length of terms, these absorbers, these air contactors, have a cross-sectional area. That's the area perpendicular to the airflow, and then they have the depth, or sometimes if they're on their side, it will be a height of the contactor. And just to compare these contactors with what we see in regular carbon capture and storage, on the left of the slide here, we see the Petronova plant in Texas. This is captured from a coal-fired power plant. In the red oval there, that's the absorber that you have. And this plant, that absorber is capable of capturing 1.6 million tons of CO2 per year. And if you look at the aspect ratio, which is, say, the height of the column versus, to get the cross-sectional area on the same dimensions, we'll take the square root of the cross-sectional area, you'll see the height is greater than the cross-sectional area here. Well, in direct air capture, the situation is reversed. On the right here, we see Climeworks. This is a 900 ton per year capture unit. And you can see the depth is fairly small, and the cross-sectional area, basically the area we see behind all those fans there, is bigger. Now, you'll see that this is only 900 tons per year. If you're going to do the same as you're going to do at the Petronova plant, you need about 1,800 of these units running. So you can see the scale that this is causing. And of course, that's a lot of steel and other materials that go into the capital cost. We can quantify exactly what the cross-sectional area you need. If we're going to say, this is example here, we're taking the concentration of CO2 in the air is 410 ppm. We're going to have do 1 million tons of CO2 per year capture, and we're going to assume the utilization rate of our capture plant is 90%. You have two other variables, the linear velocity, that's how fast the air is throwing through the contactor. For absorbers in general, it's in the range of 1 to 5 meters per second. And you also, how much of the CO2 you capture from any given volume of air. And I show it for several ones from 50% to 90% here. The carbon engineering design, which was discussed in the Joule magazine, the Joule journal, from carbon engineering, had a linear velocity of 1.4 meters per second and a capture fraction of about 75%. That gives us a cross-sectional area of 46,000 square meters. Well, what's 46,000 square meters? Let's put that in perspective. It's basically, if you had a structure 10 meters tall, it would be almost 3 miles long. So 10 meters tall, about a 3-story building, 3 miles long. So this is very large. You'll break it down and use multiple contactors. And one thing you have to do now is space the contactors. I say this analogous to a wind farm. When you build windmills, you don't want it in the wind shadow of another windmill. So you have to space them out. Here, you don't want one contactor sucking in the depleted air from another one. And you need to know this number to understand the land areas. Unfortunately, in the literature, I haven't seen any detailed study. You go in literature, you see lots of studies on wind, on how you do the spacing. I haven't seen that at all for direct air capture. There was a National Academy study that says, oh, they gave a range 1 to 7 kilometers squared for 1 million tons. But once again, I haven't seen anything based on what I would say you need some sort of atmospheric dispersion modeling to do that. And maybe David in the next talk may address this issue a little. You also need to connect these contactors. You need to put energy into them. You need to take CO2 out of them. For the liquid absorption systems, you need to put solvents in. You have to have instrumentation. And the other thing you need to do is keep the pressure drop very, very low. So you're putting a lot of air through here, and the power to put that air in is proportional to the volumetric flow times the pressure drop. So a small change in pressure drop can give you a big change in the power you needed to move that air. So these are the requirements of the contactor. Now let's look at energy. If you go into the literature, and actually it's based on a little more than literature, these are some numbers from the Climeworks unit, but also in the literature, it's fairly consistent for other capture processes out there. You need about 1,200 kilowatt hours per ton of CO2. Sometimes these numbers don't include compression, but I've adjusted everything because you need to really compress the CO2 coming out of these units. Climeworks has one going to a greenhouse. You don't have to compress there, but if you want to do it for to store or for other reasons, you are going to have to compress. To keep the cost of these negative emissions from becoming excessive, you have to use very low or zero carbon source energy. And as an example, if I'm next to a coal-fired power plant, I'm using the electricity from that plant to power my direct air capture unit. I'm going to generate 1.2 tons of CO2 for every ton of CO2 I take out of the air. Obviously, that's a non-starter. I should have said something else at the beginning here. I've done this all on a power basis. I mean, some systems use both, other energy sources, including power and heat. Climeworks, for instance, uses both power and heat, but they also talk about using all power and using a heat pump to generate the heat that they need from the electricity. So things can change, but for the illustrative purposes of the magnitude of the energy we're going to need, we go through this exercise. Now, if you used a gas-fired power plant, now you're only going to put out about half a ton of CO2 for every one you capture. But this has a big impact on cost. So if direct air capture, someone says, well, I can capture CO2 for X dollars a ton of CO2, and this is how much per ton I capture. That's not really the number we're interested in. We're interested in how much CO2 you avoid. So you have to really look at the net you capture. So instead of, if I capture 1 ton, I only net 0.5. This basically doubles the cost of the capture cost into an avoided cost. So it's very important to look at the life cycle of these to understand. Well, let's take a look. Let's put 1,200 kilowatt hours per ton of CO2 in perspective. If we're going to capture 1 billion tons here, and 1 billion tons is a little less than 20% of the CO2 put out by the US every year. And the yellow bar, and that's the red line, the yellow bars here are the generation of electricity in the US in 2019. You could see that to capture about less than 20% of our emissions would take just about all of our carbon-free energy, maybe 80% of it, between nuclear, renewables, and hydrogen. So it's a lot of energy to do this, but at the same time, we want more carbon-free energy because we want to get rid of our coal and gas on this graph. Nuclear are going to be retiring. We want to replace those with carbon-free energy. We need to increase our electricity to charge our electric vehicles. We want to power our heat pumps. And don't forget, there's a big movement in green energy these days, so we need electricity for that to do our electrolyzers. And of course, we want some power for direct air capture. So this scale is monumental, and it's something I think, you hear a number 1,200 kilowatts per ton, but when you start looking at it this way, you really start seeing the scale of the problem. All right, let's come to cost. And so just to be clear, as I said before, but I'm going to say it here, there's no question we can technically do it because there are commercial units operating today. The real question is one of cost. Oops, let me go back. So before I do that, I want to talk about, when you read the literature, there's been a lot of what I call cost myths out there. People say this is great because this has these things going to reduce cost. Well, the first thing is people say, because we use air as a feed stream, we can put a DAC plant anywhere. Well, siting is a very complex problem. Items like land availability, access to low carbon energy and other utilities like water, permitting issues, acceptable meteorological conditions, and a lot of these processes, the ambient meteorological conditions do it. I just saw an article the other day that Climeworks in their new process up in Iceland had trouble when the weather got cold, and they actually had to shut down and make some modifications on their things. All of these can be handled, but it just adds money. Accessibility of CO2 storage options, all put constraints on the siting of DAC. So siting of DAC units, especially when we start getting to large scale, is going to not be simple. There's another cost myth. There's unlimited feedstock of air, so we're free to choose the capture fraction you want. And as a process engineer, this is the one that drove me crazy, more crazy than any of them. The optimal capture fraction is really a dependent variable in the design, not an independent one. It comes from trade-offs and other things. So if we have a capture fraction, we'll go to a higher capture fraction, that will decrease the amount of air process. It will decrease the cross-sectional area, but it will increase the contactor depth and the pressure drop. So when you do the engineering, there becomes a sweet spot. And looking through the literature from Climeworks and carbon engineering, it looks like that sweet spot's in 60 to 75, 80% range. Now, that could change with other designs, but that's what I'm seeing so far from the literature. Oops. And finally, people say, well, we can use if we're using thermal energy for regeneration, 100 degrees C, that can be supplied by waste heat. And this is for approaches like Climeworks or Global Thermostat. But we can have a discussion whether 100 degrees C is waste heat or not. But in any case, there may be some opportunities to take advantage of excess thermal energy. But when you start doing this on a gigaton scale, which people want to do, those opportunities are going to be a very small fraction. So now, what's the cost? And I saw, Steven, you had a 375 as your high estimate. You're going to have to revise your slide, I think. So you can buy negative emissions today from direct air capture. You go to Climeworks website, and they're selling them for $1,200 a ton of CO2. There are many papers, articles quoting a range of $100 to $300 per ton. I just don't find these estimates credible for the reasons I have here, but I've also had more in-depth analysis I can't talk, don't have time to talk about now. If you were going to ask me what I thought would be in 2030 the cost, I would guess a range of $600 to $1,000 per ton of CO2 removed, per net ton of CO2 removed. So this is an avoided cost. So this is the real number we're looking at. I recently wrote a book chapter, and this book on negative emissions is going to be published in August of this year. And I'd be happy to send anybody here a copy of that chapter. It has more details on what I've talked about here today. And after that, turn it over to David.
So first of all, thanks to Seb for helping to put this together, to Steve for introducing, and to Jake, and thanks especially to Howie for speaking. And I really want to especially emphasize how important it is in this world, especially in the US, with this sort of ridiculous amount of polarization, to be able to have a respectful kind of fact-based dialogue is really a treat. I think that is the right word. And I expect that to happen here because I've got a huge respect for the work that Howard has done. He helped to get me started in working in CCS towards the end of the last century. So I guess a preview, an obvious question is, if you want to know about the costs of industrial technologies, should you believe an MIT professor or a Harvard engineer? And the obvious answer is going to be the Harvard engineer, but I've got a slightly different answer, and it's not the one you expect. Let me get some things I agree with first. Direct air capture DAC is high on a hype cycle right now, no question. You can see that so clearly because direct air capture is becoming synonymous with carbon removal in a way that like forgets there is any other carbon removal. No question that's true. Howard mentioned three myths. Two of them are dead on. So absolutely agree that this capture fraction adjustability, completely agree with what he said. And you're right, you're no way you're going to do this with free energy. There's literally engineers employed industrial processes to go look for free thermal energy. It's just not there in that quantity. Complete agreement. On the last one, I actually really don't agree, though maybe that we're not that far apart when you think about overstatements. To be absolutely clear, if you go and build in the same construction cost environment, in the same energy cost environment, a DAC plant and say, post-combustion on a cement plant, there's no question that it's going to be much cheaper to do post-combustion on a cement plant. No question at all. So now let me get a little bit to kind of the core of this, and I'll get to some of the specific technical answers, but I want to start with trying to get to my kind of answering my rhetorical question of who should you believe? I think my answer is neither. If academics were able to tell the costs of industrial technology that had not yet been developed by just doing some little calculations in their office, they would get gigantic money from Wall Street. So I came to Harvard from University of Calgary Petroleum Engineering. And although the overall brain power at Harvard is higher than UC, what you have at Calgary and here at MIT is a real disconnect between the world here and the practical industrial world of what stuff actually costs. Because to figure out what direct air capture costs, it's not about theory, it's about actually figuring out component by component, unit operation by unit operation, what they cost. And you can't go look that up. So if I think about the early days of carbon engineering, where we desperately need to know what a certain kind of contactor would cost, we have no way to find out. It's not in the literature. And if you go talk to the biggest manufacturers, and we're a little 10-person startup at that point, now we're a 150-person startup, it's different. But a 10-person startup, they just go away. it's very, very hard to know what business costs. And if you're, academic sitting at MIT, so what if you're at MIT? It doesn't magically tell you what things cost. Costing things requires deep, detailed engagement with engineering hours and with being able to know through the supplier network what the actual current costs of real things are in a real place. It would be wonderful if we could figure out in advance what things cost. We just can't. It's just not a thing we could do. And I think all of us in the energy business who opine about what things cost in the future need to have a little humility about how hard it is to figure out what things cost until they're actually in the market. So if I have anything to say about costs for DAC, and I've got a bunch of specific answers, but I have anything to say, it's simply to turn to what the partners of carbon engineering, Oxy Low Carbon Ventures, which is a top-level business unit of Oxy Petroleum, what they've said publicly. And again, I'm started as an academic. I tend to not take business that seriously, but now that I'm a little further into it, I understand the deep difference between what a startup company says and what a publicly listed company says with all the checks and balances that implies. So if I farm a startup company tomorrow, I can say that I could do DAC for $1 a ton. Nobody's going to arrest me. I could say that I'm going to make myself look better than Brad Pitt. It just doesn't matter what I say. There's no rules. I can say anything. But if I'm a publicly listed company and I'm the president of that company and I'm going to say what our new technology costs, I do that only after a giant amount. In the case of the current DAC-1 plant carbon engineering, I just checked last night, we've now burned through 250,000 hours of engineering time. That's the kind of work it takes to figure out what stuff costs. So at this point, we're through FEL 1, 2, and 3. We're basically at the end of the FEED study right before final investment decision, which of course still might not happen, who knows? But what Oxy has publicly said, and you could all go look at it in the Oxy event in March, what they publicly said is the cost for this first 500,000 ton a year train is between $300 and $425 a ton CO2. And there's a lot of conservatism in that estimate. And that estimate is definitely, Howard was asking, have we done, do we know how quickly you can pack them together? Just to pick up a specific technical question, is it 1 square kilometer per million ton per year or 7 square kilometers per million tons per year? So the answer for that plant is it's a little under 1 square kilometer per million tons per year for that plant. And did we do the CFD to look at it? Oh yeah. And because that's kind of from my field, it was something that really pissed me off. I thought we weren't doing carefully enough inside CE. So there's been a lot of CFD, like elaborately doing this, looking at wind conditions, looking at different wind conditions. And to be clear, for the internal numbers that we quote, like how big the contractor has to be, it's derated for our average expectation in the real conditions, in the real place of what the actual losses are. We're stupid, but we're not that stupid. When people do 250,000 hours of engineering, they don't forget stuff like, is there a reingestion? So I think the truth still is that we don't know. Maybe that plant will fail. I'm pretty optimistic, but it might fail. I think actually the probability of the costs being twice as high is almost zero. In the sense at this point, you're looking at vendor quotes. And the people, don't trust me, but the people who are in charge of that build, carbon engineering is still a little 150-person startup, but we're not the ones who really understand costing. I'd say if there was a place where I most thought our company would fail, it was when Oxy first and some other parties first looked really deep into the details. Because from the beginning of the company, I actually listened a lot to Howie, in fact, and other people like him. And I tried to be conservative all the way through. We built that company in a culture of fear because we had the American Physical Society and everybody else telling us we were idiots, that the cost was really $1,000 a ton. So we built all this conservatism in. But I still wasn't sure if it was true, because in the end, we were a bunch of young people. None of us, not true now, now we've got people who have, but early on in carbon engineering, nobody in the company had themselves built $1 billion project. Now we have some people, of course, who have, but I haven't. But the people who are doing the costing at Oxy, many of them have built many such projects. And they look at our project, they say, it's not so hard. And when they first really looked at us is when I thought if there was a time we were going to fail, it's when they found some big problems. They found a whole lot of problems. There are a whole bunch of stuff that we've done were wrong, but they're also finding all sorts of ways we can be cheaper. They found us like much better vendors than we had and clever ways to do the air contactor we didn't think about before. That's been really not just through Oxy, but through bringing in other vendors that they've gone out and looked for that we hadn't found. It's really very exciting to see how it looks. So I can't tell you for sure what it'll cost. In some sense, nobody can. But I think the probability just to kind of summarize, and then I'll come back to some more specifics. I think the probability that it's 600 or 1,000, given where we are in this close to front-end decision of a full commercial plant that's really been thoroughly costed. I mean, how we had questions, sensible questions about like how hard do you space the contactors and have you thought about the cost of piping and so on? The answer is yes, agonizingly. There's been a whole creative destruction where you have one design, then you kill it and change it, and there's been iterative cycles of that to deal with those costs, and they're real. And in fact, it's important to say that what the carbon sharing technology isn't exactly what we said there. So part of the stuff that Howie said is from the Holmes and Keith paper that shows the trade-offs in our contactor. The trade-offs in that paper, I think, are exactly right. They're not very complicated. It's exactly the same as Howard would say. It's a trade-off about energy of blowing the air, cost of the packing, cost of building vertical, cost of land. It's all those things. When you actually do the trade-offs, you come out a little different. And at the level of, our first plant actually happens to be where we're enough above sea level, there's 10% less air, and that actually matters. So we're sort of starting to re-optimize all that stuff. Oxy has also said that they think there's a market, and this is again in a formal public statement, they think there's a market by 2035 to build 70 million ton a year plants with current policy. They have a higher case with more policy, but with current policy, they think they can sell that. And I think one thing I can say is, well, I can't say the number, but I think it's very effective for Howard to say the only real price is to go on the website of Climeworks at $1,100 a ton. So I guess that's the only real fully publicly disclosed price, but it is publicly disclosed that we sold Airbus 0.4 million tons of pure removal. And so we're not doing EOR, that's pure removal. The cost isn't public for that deal, but it is a long way under $1,000 a ton. So that, and more of those things I think will become public, but I can't tell you the number. That's the part of business I hate. I like the professor world where you can say everything. I think no one knows where it goes from there, and it's certainly possible that the first plants have problems. But I personally, given the state of that, have real optimism that the price, or not optimism, some confidence, the price is kind of in that realm where Oxy's saying. And remember, that's what they're saying for the first 500,000 ton a year train. They're planning to build a second, and they've got lots of ideas that aren't like just vague academic learning curves, specific ideas for how they cost down from there. How close it gets to $100 a ton, I think is really hard to guess. My personal sense, but this is me doing just what I told you not to do. As I said, like academics can't do costing. This is me not doing what I've just been talking about, but just frankly winging it. My personal guess is that getting under 100 is really hard. I think there are ways in which there are a lot of startup companies claiming like 50, but I know that if you just take the core of the contactor and everything else is free, if you just have to pay for the structure and the land and fans and everything else is free, it's actually hard to get much under 50. So I think there really is a floor somewhere there. But I think that if you ask me, can we get under like 400 or 500? I just don't see. I mean, maybe carbon engineering blows it somehow, but I think I know enough that I'm really confident because there's just so many shots on goal. And I think the key part for me is knowledge that we can make our liquid-based system cheap. And that really is the key. And I'm happy to come back in Q&A why I think a liquid-based system is really a fundamentally good design choice. And I guess, sorry, one more thing on that, and I'll come up to some other specific answers. So it's, I think, important to say that even in, say, Steve, wherever he is, Steve's presentation, he implied that liquid DAC equals the carbon engineering calcium loop. I don't think it does. So we're proud of the calcium loop. It allows us to come to market with 1 million ton a year process now. But we totally get all the bad things about calcium. And we get them much more than anybody else because we're living with them. It's awful. So to be clear, it's awful, but it's better than anything anybody else can do now. But we are absolutely thinking about liquid processes beyond calcium, of course. And indeed, in a world, and I'll come to that, where electricity from solar in the cheapest place in the world is getting so cheap, of course, we're thinking hard about electrolytic methods. And it really is changing compared to where it is. So I do think that an aqueous DAC is going to win. But I don't think it's going to be the calcium process of the long pathway ahead. It's going to be other aqueous processes. There are other developers as well as carbon engineering doing that. So I think it's important to think about what I think of as the two platform technologies, solid and liquid platform technologies. Okay, a few more specific things. One that actually Howard didn't bring up now, but is in some papers, I think is for those of you sort of coming from chemical engineering background, is really important, is scaling. So how much are we scaling up from our current plant? because that's an obvious thing in questioning how real we are. So I think it's important to say there are three big unit operations, and it's really the risk of each of those unit operations. Of course, there's risks of coupling, but the coupling is not too tight for this thing. It's not like advanced chemical process. So for the contactor, in many senses, our scaling is one. I mean, the current contactor, not the old one, but the contactor that's now on the CESE site at Carbon Engineering is basically the same as our commercial contactors. The commercial one's now going to be a bit different, but it's not significantly different in height or packing. So we really aren't scaling the contactor significantly. All we're doing is doing multiple units. And that, to me, by the way, it's the thing that I most like about Carbon Engineering technology. We get to take all the advantage of modular construction where it's useful in the contactor, and we get to take all the advantages of economies of scale where it's useful in the back end. So the contactor scaling is about one. The pellet reactor scaling is in diameter of the vessel, it's about 1.8, and in flow, it's about 4. So it's not that big a scale up. The calciner scale up is huge, no question. On the other hand, people have built commercial calciners for a long time, and they build oxy-fuel. So there's definitely risks, but I think they're risks that we have under control in a reasonable way. That's our land. So let me come to siting, and then I want to come back to some kind of positive things that aren't just answering, but are talking kind of differently about how to think about these technologies. So I said that I agreed with two of Howie's myths completely. On location, I think he's absolutely right to say that there's a bunch of flaky stuff in the DAC literature here that just sort of says we can site them anywhere. And you're absolutely right to say siting is really hard. I mean, seeing it from inside a company, man, siting is really hard. All these details are endless. But I do think there's a profound way in which the freedom to site really does matter. And I think it matters in the context that energy costs are, if anything, becoming more unequal in the world than they used to be. So the fact that we can now build solar in the real world, no subsidy in really sunny places, it costs under $10 a megawatt hour. You look at the cheapest big projects in the Middle East, they're going in at that cost. And yet Europeans are paying, somebody can tell me, Europeans are paying like $100 a megawatt hour now. It's ridiculous. So there's huge asymmetries in cost, and I don't think they're going to go away quickly. It'd be nice if we could run big electric cables, one of my current excitements, from sunny places to northern climes, but we're not going to do that quickly. So these asymmetries are going to be big. And I think it is actually important in thinking about air capture to have some siting freedom. The world is not a copper plate. The reason that free trade makes the economy go faster is there are inequalities in what things cost in the world, and free trade evens them out. And that is deep. And the business of having some freedom to put things, that is not a myth. It is a reality. That's why trade works. And to think a little more specifically about it, in general, I said before that if you think about building a DAC plant versus building CCS on an industrial facility, and you have the same energy costs, same capital construction costs, which is cheaper, of course, CCS in the industrial facility. But if you're talking industrial facility in the middle of Europe, where land is expensive, where other things are expensive, where it happens to be in a running plant that you don't want to shut down, versus a DAC plant where you're building big multiple modules of the same plant and you're building solar or wind to match it, it's not clear how that's going to come out. It really depends on the details, but in some cases, DAC might win, even though it's inherently cheaper to do post-combustion capture, all else being equal. I don't know how it'll play out. Nobody does. So let me end with some ideas about how DAC might matter. So I don't think we're going to build 1 billion tons a year of removal soon. There's no question that the near-term focus should be on cutting emissions. And in general, the first rule of holes is to stop digging. So I think there is a kind of overclaim around carbon removal that's going to like substitute for cutting emissions. It doesn't make sense. But I think there's a way in which actually DAC could be surprisingly important, even if it's not that big in the near term. So maybe Howard will turn out to be right, but let's say that it's true that costs really come out at, choose a number, but a number like 250, maybe it's 350, in the relatively near term. So like later this decade, we actually can build multiple million-ton-a-year plants, and that's what they cost. I think that will actually be important. Now, to be clear, that's still a lot higher than the social cost of carbon. It's a lot higher than the McKinsey curve cost of cutting emissions, but it's lower than a lot of things humans are actually doing today to cut emissions. And I think that having a real cost that is a pure negative emission cost could help impose a kind of cost discipline. In the climate debate where we've got everybody rushing to do stuff on climate, people are doing a lot of stuff which doesn't make much sense, which costs $1,000 a ton carbon. But right now, there's no pure negative emission that's verified that you can buy. If there really is one, that may help beyond its direct benefit. It may help to impose some cost discipline on people's thinking about mitigation policy in a way that I think could really be useful. For example, me, fancy green Harvard professor, my wife and I are building a house in Camera, Alberta, long-term home, and we have no gas line, which I'm kind of proud of. We have geothermal. We have extremely nice 0.5 watts per square meter per degree Kelvin per square meter windows that we bought from Europe. If I'm honest about those windows, and it's a cost plus contract, so I can see the different window quotes, it's like over $1,000 a ton buying those windows. And many other things about my house are like that. And lots of things that we do, lots of people's fancy electric cars in places that aren't there are over $1,000 a ton. Offshore wind in this, which is a lot of what Massachusetts is going to avoid, is going to be well over the cost of air capture, if I'm right. I think there's something useful about it's coming back to fuels and solar. I've been involved in energy and climate now for more than 30 years. And sometimes it's interesting where things that you thought were true for a long time just aren't true anymore. I spent so much time thinking solar was overhyped, that it was moving slowly, thinking of it as being expensive. I think we really are moving into a world where in some places, and only during the day, not everywhere, the world isn't a copper plate, electricity, carbon-free electricity just becomes really cheap. And the key is to figure out how to use that really cheap energy to decarbonize. And some of it will be by long distance transportation. Some will be bringing manufactured there. But I think one of the pathways will be bringing fuels manufactured there. And for that, DAC is important. And picking up on Steve's slide, Steve showed you that if at $80 a ton, according to Steve's slide, it was 0.2 bucks per liter, of which he has a total budget of around $2 per liter. So even if he had double the 80, maybe he's too optimistic, and by the time this is really done, it's 160. And again, I'm not talking about now, I'm talking about late 2030s towards 2040. That's still pretty small. And the key thing is that the solar being really cheap and electrolysis getting cheap allows you to do that in a way that really is a different thing than we could have done before. So thanks, look forward to the conversation back and forth.
So before I turn to questions, let me just first see if there's any interaction that we ought to just on this discussion we've had thus far. Any comments one way or the other?
Okay.
Howie, please.
All right. So first of all, thank David for his talk. And I should say I actually visited the pilot plant in December of 2019, a few months before COVID hit, up in Squamish, British Columbia. And I was very impressed with the engineers there and what they were doing. And I wish the best of luck, because if it happens, I think it's a benefit for a lot of people. I also agree with David that no one really knows cost. I mean, I, for so long, tried to avoid giving a cost number, but it's sort of like you only could avoid it for so long. And so that's why I gave the range. And it's very important to know that the same technology built in different places, different things. And I write the cost numbers by themselves are totally meaningless. You have to know what's the cost of capital, what's the cost of fuel, what's the cost of a labor. So all of that matters. And of course, the costs from 2 years ago are totally different from the costs for today due to things beyond all of our control. So I think that's important. Another thing about saying using cheap solar to run this, I think there's two issues you've got to consider. Direct air capture plants are fairly capital intensive, and therefore they really need to be run 24/7. So solar, even in the Saudi desert, somewhere, still under 30% availability factor. So if you're going to use this, you're going to need storage in there. And that, of course, starts raising the price. And even with storage, you're not going to get 100 or 90% utilization factor, because then the storage cost becomes too much. So that's one issue. And also, this isn't going to be in a vacuum. So right now, people want to do solar in the Saudi desert. In fact, there's been an announced project to make green hydrogen. I think they're going to turn into ammonia and ship it to Japan. So there is competition. Now, I don't want to get into the cost benefit of better to do hydrogen or direct air capture. I haven't done that work, and I'm not even going to try to guess on that number. But just to say this isn't being done in a vacuum, that there's solar can be cheap today at certain things, but if we have arbitrage, natural gas is pretty cheap in this country. So we started building LNG terminals, and now we're building more, and I'm dreading next winter with my natural gas bill coming up. So anyways, that's a few things. And one last thing, I'm very happy that Oxy is doing all this work. And I think that's the best way to know. Actually try it. And especially when it's not my money. So, but
here.
just because Oxy's doing this and say in a feed study, we're going to do this. So the thing that I talked about this in my chapter, because I was close to this project too, the Kemper County project in Mississippi by Southern Company, coal gasification with carbon capture. The original estimate was 2.2 billion. Eventually, they spent over $7 billion on this project, and at least the coal gasification never started. It's the world's most expensive natural gas combined cycle power plant. So there's risk with all of these things, and I'm not going to say I don't have the information to judge. So I say we'll wait and see. And I think I think it's good that we're going to see how this is going to turn out.
I'll just give a
Quick response and then a question.
Yeah, I think I lose sleep over experiences like Kemper. I don't want to say we know it's going to work. I think that's the reality. There's some way in which you can do a really good job of feed study, have a good company, and still blow it. That's the real world. I will say one thing about solar and storage. I think absolutely, of course, you got to count. And I think the real challenge for anybody building any industrial process is that everybody wants to take advantage of cheap solar. Everybody wants the grid to magically supply dispatchable power. The key is to think about designing your process so you are more able to take advantage of variable power than your competitors. That is really the key of it. And I think there's one really interesting thing. I'm not giving away any big secrets here. That as you start to think about electrolytic processes, in electrolytic process where a big chunk of the capital cost is the membrane, and the membrane has a certain number of hours, which is in fact often true, then you have different economics. So if you pay for something that has where most of what you're paying for is the bank's cost, you're paying interest on it, then when it's night and it's not running, you're paying the bank, and that's a really bad deal. But if you're running an electrolytic process where a dominant cost is membrane replacement, then at night, membrane isn't, then you can basically much more afford to follow load. In some ways, that's making a silk purse out of a sow's ear because you're dealing with the fact those membranes are expensive. But it does in some important ways, and that's true for a bunch of processes, as you start to think truly about using electrons as cheap reagents and think about electrolytic processes, you think differently if you're trying to match solar.
So we've covered a tremendous amount of ground here, and almost any question is okay. So what about, I saw a hand in the back. Yes, in the back, way in the back.
Thank you for the presentation. It's been really insightful, and I appreciate also talking a little bit about the capacity factor of the renewable energy, because some of the modeling that we've done, we've found that can be pretty significant in terms of the overall costs. I guess one thing that I'm hoping to hear a little more about is the storage method. So we've talked a lot about pulling the carbon out of the atmosphere, but I'm curious to know some of the thoughts about, or maybe the current status in terms of what we plan to do with the carbon once it's pulled out, and maybe some of the challenges there too. And then I have more of a comment too. There's been a lot of talk about going to the cheapest sources of energy globally to really make this cost competitive. I just want to make mention that there could be some very serious equity concerns too, and I want to make sure that the room is aware of that.
Sure. So you want to respond to that?
I'm going to tell you, I mean, I'm hard of hearing, and I didn't catch the whole question. Can you repeat it?
One question is about security of storage and how geological
So the
storage
question
works.
is, let me back up. So the first question, the second question was, when you're looking for the least cost, you don't want just a pure dollar measure. There are lots of equity issues and what you mean by cost in terms of equity. That was, I think, the second point. It's not just the dollars.
I'll
It's
come to
more.
that if you like.
But the other question was about
But storage, yeah.
So it's true with BECCS, the biology with capturing storage. It's true with, and if you have these technology, you're getting CO2 and you're concentrating and you have a concentrated liquid. Do we have any plan? Do we have a likely plan for where we're going to put it outside the current use, which is mainly in enhanced oil recovery, putting it back in oil fields? You want to respond to that, Howie?
Geologic storage reservoirs, I think, are the main place to put the CO2. We're doing it now on a relatively small scale, millions of tons a year, tens of millions of tons a year. I think we need more experience. The bipartisan infrastructure bill is setting up 4 hubs for 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 CO2 storage underground. And, there's a lot, especially in Houston, they're really jumping on that, want to make a hub that's over 100 million tons a year. So I think the technology's there, there are some risks, but the geologists I spoke with, I think they all could be managed, and this can be pretty secure place to put it. In terms of utilization, I have my real doubts about that. And partly is if you're going to, well, you take the CO2 out of the air and make fuel, what you have to compare that with, because it's fairly complex process to go from the CO2, then you need the electrolytic hydrogen, then you have to synthesize through the Fischer tropes, and then you have to refine it to get to your final fuels. A lot of times I think you may be better off just using the jet fuel you have today, which are already been optimized, and using things like direct air capture or other negative emissions to offset it. So that's my view on that point.
No question here.
Can I answer on the equity issue?
No.
I think it's important. So thanks for raising it. I taught a really exciting course at the K School with a bunch of mid-careers this year, and one of them wrote a really thoughtful essay trying to think through the equity issues of cheap solar. So thinking about the fact that Europe, if it really wants to decarbonize, will want to put a whole lot of solar in North Africa. Who controls that resource? How is that different from pre-1972 imperial control, if you like, of the oil producing countries? And I think there's not an easy answer, but I think it's a good question. Obviously, the happy answer is that this actually is a benefit in terms of job and development in some places, and it could be, but I don't think it automatically is. And I think we have to really think hard about who controls and who gets the resource rents from those developments.
Please.
My name is Jacoby. I'm the founder and CEO of World Energy.
Oh, thank you. Hi, my name is Gene Gabolos. I'm founder and CEO of a company called World Energy. We're the first producers of SAF in the world and still the only in the US. Florian, thank you so much for the invitation to come. You guys were fantastic. This was really great. And I can't tell you how impressed I was, not only with the material, but with the way you dealt with differences of views. So kudos to all of you guys. We're wrestling right now. And to your point about cost, I just want to bring some, industry data to it. We are in the middle of a $2 billion expansion of our refinery in LA to produce 370 million gallons or so of SAF. We originally
explain what SAF is.
Oh, sustainable aviation fuel. I'm sorry, and we're currently making it out of non-food feedstocks.
This is biological.
Yes.
Source, which is what?
Animal fats, used cooking oil. We have the ability to use virgin vegetable oils, but don't currently. But certainly, we'll have the option to do it over time. So, in any case, we originally estimated that project to be about $800 million. We had Fluor and many other engineers we are working to help us get to that number. We're now at $2 billion. This is not.
But does it originally mean at FEL3? At what point?
At what point?
What does it originally mean?
We were at FID.
So
when we were at 800.
I think for the general audience, you're going to have to explain this technology. Do you want to comment on this, Steve? About
Well, I think we have a short question here.
Yeah. I'm sorry. So this does turn into a question, and so and I just want to give some sense. We're also tomorrow in the provincial register in Canada. We will be announcing that we've submitted permits for a very large wind project that will go to green hydrogen. Green hydrogen, for all the talk about green hydrogen, there's only one major plant in development. It's Air Products plant in Saudi Arabia, and so there's lots and lots of talk. Anyway, we're doing that with an eye towards sustainable aviation fuel, and the notion is to capture carbon in the U.S., probably Houston, more likely Louisiana, but in the Gulf, and then move it to in the northeast of Canada, where we've got really good wind resource, and then produce sustainable aviation fuel there. Why? We haven't really gotten into how complex it is to move this stuff. So to move green hydrogen it's great to be able to produce it wherever the wind. I think you made the point about solar being wherever solar is. Wind is also wherever wind is, right? And it's not even everywhere. So a lot of this stuff will end up getting produced in remote locations. Then the question is, how do you move it from the remote location? You mentioned the wire to Europe isn't so great. So I'm wondering if you can just opine on what we're working on, which is to produce sustainable aviation fuel where the wind is, where we can get to the green hydrogen.
Steve, I think this is for you. Comment.
I'm not sure. I mean, I think it sounds promising in the sense that you want to reduce the hydrogen where you have the cheap electricity that's green, right? So from that perspective, what else would you do? I think the debate with hydrogen production use is, do you do the production centralized and distributed, or is it cheaper to produce the hydrogen in a distributed way? And I don't think there's really a clear answer yet, although I think it's sort of moving towards that you probably have to have distributed production because of the costs of moving stuff around that you talk about. Although, you know, somebody may prove that wrong at some point. Maybe you will, right? But I mean, early on, probably what you're doing makes sense for the plant 1 or 2, right? But for plant 1,000, maybe that's not the same. What are your thoughts? You probably have some.
Just one thing for the audience. So sorry about the acronyms. FEL, front-end loading, a standard piece of process design. FID, final investment decision, when usually there's a authority to spend money in a major company. So you're talking about moving the hydrogen, correct? Or the CO2? That was a little unclear.
What I'm asking you is,
Yeah.
moving the hydrogen is complex.
Yeah.
Right? It requires conversion to ammonia. You got to put it in
Yeah.
pressurized ships. You got to reconvert it back to hydrogen, and then you displace the natural gas wherever it is. So I'm just wondering generally, because it's so expensive to move green hydrogen, and all this power generation, whether it's DAC or hydrogen generation or whatever it is, it's all based on how cheap can you get the green power, right?
So I think the answer is hydrogen is in some ways not a great fuel at whatever, 240 kilojoules a mole. It's just like hard to compress, hard to move, and brittles metals. It's great in some places where you use it, but it just isn't a very good fuel. And so my personal guess, and I don't know, there's ways it could go differently, is that we never actually move a lot of hydrogen a long way. I think we move electricity a long way. I think we use hydrogen to make things, ammonia or fuels, and we move the ammonia or fuels. And, you know, again, thinking of this place where Steve opened, the cost of DAC as a fraction of the total cost of making synthetic fuels is actually pretty small. I mean, it's not small if it's $1,000, but it's small if it's sort of 200-ish. And moving fuels is so much easier than moving hydrogen. Easy to store and move, and you've got the compatibility. I think that's mostly what we do. Of course, there will be some cases to use hydrogen, but I don't think that many.
And just going back to a point Howard alludes to about, you know, the hydrogen versus synthetic fuels. I mean, in a sense, it's a big technological bet if you're in an industry like aviation. It's do you bet on David and Carbon Engineering and their competitors in being successful at making DAC work at large scale to produce the carbon we need for synthetic fuels, or do you bet on you know, Airbus with the vision for hydrogen aircraft and also all the things that come with that, the sort of large scale hydrogen production and distribution, which, as we discussed, is challenging, and, you know, making a new safe system and so on. So they're both very challenging things to do. They're both technically possible, and it kind of is in the margins now as to which one is more economically desirable. I just don't think we have a clear answer to that yet. So that's TBD.
Excuse me, we have a question from the web.
Yes, why don't we throw in a question from the web quickly? And that is actually coming back to the main question of the webinar, and the question of, we look into DAC going forward and we accept that we're at $600 or we're at $300 or whatever we are today. What can we actually do? What are our levers to get these costs down as we move forward?
Okay, let's start with Hallie. So the process engineer.
In the chapter I wrote there's a graph from that's been used from a good colleague of both David and mine, Ed Rubin, that shows when technologies are in an early stage, the price actually goes up before it comes down. So the question is, where are we in the cycle of development of this, and why do prices go up? Well, when you design something on paper, you haven't had it built out there. So the example I gave of Climeworks, well, they realize in Iceland they have to have more money come in to weatherize their system, and there's a lot of cost that as you go into more detailed design, you realize that you missed in the first time. So the costs may go up, and then you can start going down. I think, in general, I think you can do something with the cost of electricity, but I think the amount of energy you need for these systems maybe can go down a little, but not that much. I think the big area you can reduce costs is capital cost of these systems. And as David said, and I know Climeworks says the same thing, they want to do it by replication, sort of the same thing we do with solar panels, economies of scale for mass production, and the like there. So that would be my view from a
We're
way
sure
up high.
you're sure on time. A question here? Yes.
Yeah, Admir Masic, CMIT here. When it comes to hydroxides and mineralizing CO2, what are the industrial bottlenecks in terms of cost to exploit that natural absorption of CO2?
David?
I mean, gas solid reactions suck. That's one answer. I think maybe to step back, moving beyond DAC to carbon removal generally. So the fundamental thing that CO2 wants to do in the Earth system is to weather alkaline minerals. That's the long-term place it goes. And you can mine alkaline minerals at CO2 equivalent costs that are tens of bucks a ton carbon by hard rock mining. And thermodynamically, it's favored. They want to react in the ocean, thermodynamically favored, to make alkalinity that really would permanently remove the CO2. The problem is all kinetics. So literally true. If you take silicates, ultramafic rocks, grind them up to micron scale and sprinkle them in the ocean, they sink to the bottom before there's a useful reaction. So it's tough. I think it's really worth working on it, but people don't have good ways to bridge it.
But hydroxides like calcium hydroxide will absorb CO2 if
Yes,
you
but
put
we
it
don't
in a...
mine. It's not a source. You have to make calcium hydroxide by
So,
calcium.
but assuming that you can make it, is there an industrial bottleneck to that?
No, I think so. Making lime, we know how to do. It's very different from our process, or it's different from cement. Making lime, there's these beautiful kilns you can buy that on big chunks are actually 90% thermodynamically efficient. These very cool opposite flow kilns, and there are definitely pathways to do lime with CO2 capture if you started from scratch that are quite reasonably priced. And so then what you're doing is that's basically the original paper, which I think is the still one of the best pathways. It's Haroon's paper, which says you calcine limestone, you put the CO2 down whole, and then you take the CaO and put it in the ocean.
Yeah.
We're drifting into another topic.
I think
Yeah.
liming in the ocean is very interesting, and from a technical viewpoint, I'm very bullish on it. From the political and getting permits and convincing people,
I agree.
and it's hard to measure. But
Talk about my day job, man.
What?
So I mostly work on solar geo.
Yeah, I know you. But, I mean, I hope it gets a more serious look in the future. Yeah, because
We'll schedule another meeting on geoengineering. A question from the web, could we please?
Another from the web here. Basically, it's an interesting logic that's being asked here is, given we have a lot of renewable electricity, given that a lot of the cost of direct air capture is capital cost, the question here is, to get these costs down, do we just have to invest in it now? Do we just have to go for it? And is that eventually going to be the enabler of this technology, similar to how PV, for example, played out?
I don't think learning curves are not magic. They're not laws of nature. They don't necessarily happen. And I think, to call out somebody I really appreciate their work at MIT. Jessica Transik has done some really nice work showing the way learning will work differently and with different kinds of technological complexity. So I don't think you can just like magically assume learning curves. But I think the key thing is when you say the costs are capital costs and now we have cheap power, the answer is any DAC developer will optimize their system or change designs based on that power. So the point is, give us really cheap power and our capital costs will go down without any change in supplier costs because we'll just re-optimize the system. Not perfectly, but there's a bunch of trade-offs you make.
I have a chair's question about the plant we've been talking about in Texas, where you quoted the price. What is the price of electricity in that estimate? What is the electric source in that estimate?
Well, it's I can't tell you the number, but I can tell you that it's, one of the issues is I told you what Oxy released in March, but Putin invaded Ukraine before March, and it's not a secret that costs are up. So I think that's a moving target.
Well, the reason for the question is, my old engineering training that you want to watch what the free body diagram is here. Where are you drawing the lines? So it matters where the power is coming from,
Of course.
and it might be renewable power.
Yeah.
But the estimate of what the saving is, what the net saving of CO2 is, depends on what that power might have been used for in that plant. So how do they handle that?
Fundamental way. So there's sort of infinite regress arguments about life cycle, but the fundamental first order answer is life cycle should be based on where you actually got your power for under contract. And so you can contract for mixes of wind and solar in Texas that have really surprisingly high capacity factors that you can get firm contracts for. And so that's the obvious way you build it.
That's my point.
Of course, you can argue that if you didn't do that, somebody else would have used that power for something else, but they did it. If it's under contract, it was built in a sense for you.
Yeah. So I'm questioning whether the fact that it's under contract is really important in doing the social analysis of whether it really what the saving is of a plant.
I think this is partly, I think it's almost a generational thing. I think you're thinking of a world where we fundamentally are limited in our ability to make low carbon power. Whereas for me, I think we're limited in our ability
You're
to pay
making
for
an
it.
estimate for a particular plant in a particular place today.
Yeah.
That's what we're talking. We're talking about a particular plant
Yeah.
today and estimating what the cost is today.
Yeah.
Not imagining what it might have been
Correct.
in another world if that plant was in a world where we had
Of course.
infinite, where the power system was totally decarbonized.
We're definitely not imagining the power system decarbonized. This is a real
Yeah.
project making real contracts.
So if they're taking power from the Texas system, then the Texas system has a net carbon quantity per kilowatt hour. I'm just saying it, when you do these estimates, what you assume about where the power is coming and what the alternative was.
Of course.
Yeah.
Yeah. But of course. Totally agreed. Yes.
Other questions? Yes, please, in the back. Way up in the back.
Thank you very much. This has been very interesting and inspiring. I had a question about the direct air capture and if there is something external to what you're working on that could be a limiting factor to scale, that would be something that a different company might want to focus on. So for instance, I don't know if they are solvent productions or things like that. So if you think about lithium batteries and the cobalt question, so I was curious if there's anything that other people should be working on as well to enable this.
So for carbon engineering's current design, it's really hard to see things that are bottlenecks. One of the things I love about our aqueous system is the underlying contactor surface today costs $1 a square meter. Just the core, not the full contact cost, but the actual packing cost. And that's really kind of unlimited volume. And it's not anything magic, it's just PVC. So I think if we go to systems that are beyond the calcium looping system, if you go to a system that is electrolytic, then these electrolytic membranes quickly become a central bottleneck, and the scaling of that industry becomes a bottleneck. For solid DAC, for Climeworks DAC, they use more materials because you've got to build a big box that can be evacuated cyclically. So that box has to have steel and copper in it and so on, that's relatively larger amounts. And you've got these sorbents, and it depends what sorbent they use. Some of them will be hard to procure.
But no rare earth material, no rare earth minerals.
Well, not none, because I mean, we've all got electric motors and stuff. At least for us, it's not something doesn't seem like an important bottleneck.
One final question from the web.
One more from the web. And I think we're looking for rays of hope here in the web. So the question basically is, in the development of direct air capture, is there anything that we can learn from point source capture, or anything in saying scale point source capture first and take those learning, take them back to direct air capture?
So my feeling on this is if you read the literature on the direct air capture, it's all focused on the capture, but they have the same issues downstream once you get a capture. The compression, the transport, the storage is all the same. And so I think, like I mentioned, these storage hubs that are going up, it's going to be very helpful to not just point source capture, but to direct air capture. I mean, yes, you can learn things from point source capture, but you are in a very different regime because of the concentration difference. So the amines that they're using, so Climeworks is using amines just like they use at Petronova, but they're being used very differently. And so I think, there's maybe some things you can learn, but it's really the downstream that I think that you really get the synergies.
And I could add just analogously, so you're talking about the negative emissions technology and the downstreams where you can learn. And the same applies to you when you're looking at producing, say, jet fuels, where it's if you have a point source of CO2, whether it's a power station or whatever, producing a power to liquid fuel using that point source is going to be much more cost effective for a company to do in the near term than taking it from DAC most likely. So that might help to sort of decouple some of the challenges in the near term at least, but longer term, you would hope they fuse together.
Well, we've run to the end of our planned time, unless there's a final comment with any of you. Maybe I'll offer a final comment. That is that we started off saying this is an important question, and this is really an important question, since so much it really depends on this, and particularly in the plans and in the strategies that people are putting forth. And I point out that in the infrastructure bill that was passed last year, there is, what's my number?
$3.5 billion.
$3.5 billion in that bill to be spent on this technology. So what you're hearing here is a debate about what do we know about it? How costly is it? How do we go about understanding a technology that we've never moved to scale, and what that might look like, and where would you learn about that, and what's going to happen when they go to scale, and all these other issues. So this is a great, I think, terrific introduction to the audience here and the people on the web of understanding some about this issue, because it's not going to go away. We're going to be debating this for a long time. So thanks very much. Help me reward our panel for really great invitation.
Thank you.